Hi everyone, in this video we learn the different types of singularities. First we look into the analytic function. Let a function f of z be derivable at every point z epsilon neighborhood of z naught, then f of z is said to be analytic at z naught. So I have a point z naught taking epsilon neighborhood. So this is z naught epsilon, this is z naught minus epsilon. So f of z as derivatives at each and every point in this interval, then we say that f of z is analytic at z naught. If f of z is analytic at z naught, then f dash of z naught exists and f dash of z naught exists at every point in the neighborhood of z naught. If f of z is analytic at every point entire complex plane, then we say that f of z is entire function or integral function. A point at which an analytic function fails to be analytic or fails to have a derivative called singular point. For example, f of z is equals to 1 by z minus 2 is analytic everywhere except at z is equals to 2. Then this z is equals to 2 is called the singular point. Now we'll look into the different types of singularities. Isolated singularity. A point z is equals to a is called an isolated singularity of an analytic function f of z if f of z is not analytic at z is equals to a and f of z is analytic the neighborhood of z is equals to a. Let f of z is 1 by z square plus 1, then z is equals to plus or minus I or isolated singular points. Next, poles. Let z is equals to a is an isolated singularity of an analytic function f of z which contains finite number of terms in Lorentz series expansion of principal part. Suppose if it has m terms, then the singular point f of z at z is equal to a is called pole of order m. If m is equals to 1, it is called simple pole. For example, f of z is equal to z square by z minus 1 to z plus 2 whole square, then z is equal to 1 is a simple pole and z is equals to minus 1 is a pole of order 2. Next, essential singularity. Point z is equals to a is called an essential singularity of an analytic function f of z if f of z contains an infinite number of terms in Lorentz series expansion of principal part. For example, f of z is equals to e power 1 by z, then z is equal to 0 is an essential singular point. In this case, limit z tends to a, f of z does not exist. Here in this case, if limit z tends to 0, e power 1 by z, we get 1 by 0, so infinity. So e power infinity is infinity. So here the limit does not exist. So z is equal to 0 is an essential singularity for the function f of z equal to e power 1 by z. Next, a removable singularity. A point z is equal to a is called a removable singularity of an analytic function. F of z contains no terms, the Lorentz series expansion of principal part. Example, f of z is equal to 1 minus cos z by z, then z is equal to 0 is a removable singularity. In this case, the limit is existing. Next, we will go for evaluation of residues at poles. We will first define what is a residue. The coefficient of 1 by z minus a in the Lorentz series expansion f of z about the isolated singularity z is equals to a is called the residue of f of z, denoted by res is residue of f of z at z is equals to z naught. Thus, the residue of f of z at z is equals to a is b1. The coefficient b1 is given by the integral 1 by 2 pi I integral over c f of z dz. Now we go for residue at simple pole. If f of z is an analytic function as a simple pole at z is equals to z naught, then the residue is given by residue of f of z at z is equal to z naught is limit z tends to z naught, z minus z naught into f of z. Next, a residue at pole of order m. If f of z is analytic as a pole of order m at z is equal to z naught, then the residue is given by 1 by m minus 1 factorial z minus z naught dm minus 1 by dzm minus 1 z minus z naught into m to f of z. Next, residue at z is equal to z naught with the function f of z is in the form of phi of z by psi of z, where psi of z naught is equal to 0 and phi of z naught is not equal to 0, then the residue at z is equal to z naught is given by phi of z naught by psi dash of z naught. For example, if f of z is equal to tan z, which can be written as sin z by cos z, here z is equals to pi by 2 is a pole, since cos pi by 2 is 0 and sin pi by 2 is not equal to 0, then the residue is given by phi of z naught by psi dash of z naught. So derivative of the denominator function. So phi of z naught means sin pi by 2 by psi dash of z naught is minus sin pi by 2. So here the residue is minus 1. Next we will go for some problems on evaluation of residues. So problem number 1, find the poles and residues of f of z is 3z plus 1 by z plus 1 into 2z minus 1. So to get the poles, we have to equate the denominator to 0. So the poles of f of z is given by equating the denominator to 0, that is equate z plus 1 into 2z minus 1 to 0. So we get here that is equals to minus 1 and z is equals to 1 by 2. Now these two are simple poles, so we apply this formula. Now residue of f of z at z is equals to minus 1 is given by limit z tends to minus 1 z minus z naught. Here z naught is minus 1, so I get you z plus 1 to f of z. So this is equals to limit z tends to minus 1 z plus 1 multiplied with the function dz plus 1 by z plus 1 into 2z minus 1. So z plus 1 get cancels, and substituting the z is minus 1, so I get here minus 3 plus 1 by 2 into minus 1 minus 1. So minus 2 by minus 3, or this is 2 by 3. Now residue of f of z at z is equals to 1 by 2. So this is limit z tends to 1 by 2 z minus 1 by 2 to f of z. So this is by taking 1 by 2 as LCM, so I get here 1 by 2 limit z tends to 1 by 2 2z minus 1 to f of z. F of z is 3z plus 1 by z plus 1 into 2z minus 1, and substituting z is 1 by 2, so we get here 3 by 2 plus 1 by 1 by 2 plus 1. So by simplifying we get 5 by 6. Now we'll move to the problem number 2. Find the poles and residues of f of z equals to z square by z into z plus 2 to z minus 1 whole square. So by equating the denominator to 0, that is z into z plus 2 z minus 1 whole square 0. So we get z is equals to 0, z is equals to minus 2, z is equals to 1 poles. Here z is equals to 0 and z is equals to minus 2 are simple poles. The power is 1. Simple poles. And z is equals to 1, a pole 2. We have a square there. Now we need to find the residue at 3 poles. First we'll go for residue of f of z is equals to z naught. Here this z naught is, we get here limit z tends to 0 z into z. Limit z tends to 0 z into z square by z into z plus 2 z minus 1 whole square. Substituting z tends to 0, that is, here this has. Next we'll go for residue at minus 2. With z tends to 2, so z minus of minus 2, 2. 2 f of z. Putting z value, limit z tends to minus 2, z plus 2 into z square by 2 z plus l. Substituting the limits, 2 whole square 2 square. So we get here next we'll go for the residue at 1, the whole of order 2. So here m is equals to 2. We have to use formula residue z at z is equals to 1 given by 1 by minus factor it z goes to 1, m is here 2, so we get t 2 minus 1 z 2 minus 1, that is d by dz of z minus 1 whole square z. Z is your z square by into z plus 2 sin z minus 1. Go for derivative of z by z plus 2. It that tends to 1 z plus 2 square z plus 2 1 derivative of the z into the derivative of the denominator. It that tends to 1 by z plus 2 square. Then we are applying u by v, derivative of u by v. By substituting the values, we get by 1 plus 2 t square So residue of f of z at z is equal to 1 ordered to is 2 by. Now problem number 3, to get the poles, get the denominator to 0. So z minus 1 whole cube equal to 0. So that is equals to 1, the pole of order 3. Here m is equals to 3. So we substitute in the formula. So we get residue of z at that is equals to 1 1 by t minus 1 factorial limit that tends to 1 is equals to 3 d square by dz square z minus 1 cube of z, that is z into or z by z minus 1 whole cube. Z minus 1 whole cube and z minus 1 whole cube cancels, and this is by factorial 2 bit that tends to 1. Two derivatives to go. So first d by dz of z into z. To it that tends to 1 z into or z plus z, derivative of up. We are applying here again time derivative we have to go for bit that tends to 1, then we get z into or z plus e z, the derivative of first term, derivative of the second term is z as it. Substitute bits, get e by 2. Next we have some practice questions, try them. Thanks for watching this video. Like, subscribe and share it with your friends. Thank you.